Okay, this is a long, thank you for introduction. So I'm Mihailo Zărescu from the Polytechnic of Turin. I'm presenting mainly the work that is overseen by Luciano Lavagno, professor at the Polytechnic of Turin. So this long title is basically wants to say that we are trying to make available FPGA accelerators for high-performance computing data centers in a way that should be useful and easy to use by software programmers without learning new languages or hardware implementation. So basically we'll look at the outline, we'll look at CPU trends with a focus on energy and efficiency, at our toolset objectives and what have we done to do that. The clue that I already spoiled here is that we use OpenCL to design FPGAs in a way that we'll see, and then we'll look at the flow, some preliminary results, because this is an ongoing project, and I will wrap up. So, as you may already know, this is a famous picture. It was 35 years of microprocessor trend. Then it was extended by Karrup for another 5 years. So what we can see is that the number of transistors on the top line is still growing. But towards the middle of 2000, we start to hit some walls in terms of power dissipation, frequency related, of course, of the CPU, and implicitly the single thread performance. And at the very same point, the interest in logical cores started to increase in order to still increase the speed of the computation. Of course, this change in the architecture did not come as easily, as smooth as the increase in performance, because programming multiple cores, as you know, is not trivial. So, looking at the silicon, on the underlying part, we still see a gap between the silicon and the biological computation, which is at least an order of magnitude or so. At the bottom, we see the CPU, then the GPUs, which are better but still low. There are accelerators, software accelerators, which are a bit better, FPGAs, which are a lot better, and of course, then we have hardware-specific IP blocks, which are much better, but still way below the biological computation. So we are focusing on at least how to harvest the FPGAs, which are a kind of sweet point between the software programmable hardware and application-specific hardware. So the objective of the toolset are to get the advantages of low-cost non-recurring engineering costs that are specific to software-like architectures by integrating hardware accelerator in a way that make full leverage of the modern high-level synthesis tools. Another point is to accept concurrent models in a variety of languages, which will not require the software engineers to learn a new language and will make the whole flow more easily to adopt. Of course, to use this high-level synthesis to reduce the hardware design time, especially mostly by reducing the verification time, which is already an important part of any project, because the verification would be available in the domain-specific language in this case. And to improve the quality of the result of the implementation through manual and especially automated design space exploration. The advantages to map software on FPGAs we have already seen, because they reduce the energy consumption especially, and they reduce production costs because they reuse components, and they reduce at the same time the black silicon, that means the parts of the chips that are not used at any given time. Why open source in this framework? Of course, we all know about these bullets, because it builds community, because it fosters cooperation between academia and industry, and hopefully a quick adoption of interesting results. And also because open source supports industry by lowering the entry barriers, especially for SMEs, and may create jobs, including for students. Now, the basic idea is to allow multi-language input to this tool to simplify the adoption. The problem is that none of the high-level behavioral models are especially flawless for RTL synthesis. The objective would be, however, to not force to learn a new language, and for this we are looking into converting design-specific, a domain-specific model into an intermediate language which is suitable for high-level synthesis, and doing this will allow to still use the domain-specific models of the choice, and to keep happy and efficient the high-level synthesis flow. So, the point with the data center is that they consume a lot of energy for computing and also for cooling, and this is a problem, and especially so as the task for these data centers increase recently. Many data centers algorithms instead are already efficiently implemented in parallel, and are also prone to so-called embarrassing parallelism, like search, image and speech recognition, and others. And these are already efficiently coded in parallel languages. On the other hand, FPGA implementation has advantages versus processor implementation, because of the low energy and good performance at the same time, and hardware reuse, which I already mentioned. So, OpenCL in this framework has the advantage that it allows extreme parallelism and a simple programming model, which is already suitable for multi-core processing. The FPGAs have advantages because they are very energy efficient, still dynamically reprogrammable, including at the runtime, and the idea would be to use global memory that is shared between CPUs and FPGAs in a cluster, which will remove basically the problems of cache coherency, which leads to quite a bit of efficiency. You can see on the bottom part that the application, the software application is divided into kernels, computational kernels, and then it runs through a virtualization phase, which actually is splitting these kernels into threads and mapping these threads through a scheduler to hardware resources, which allow to execute this in parallel. This is what I already said, more or less. The kernels are split into independent workgroups, which are mapped to resource at runtime, and the workgroups are made of synchronized work items at this point, which share local memory. And the memory hierarchy for this project is the usual: a Groband RAM, global memory that is shared by the kernel and the host code, which is not cache synchronized, and local RAM, which is shared by work item and, of course, some private registers. Parallelization, the advantage is that parallelization is already done here by the software programmer, so we don't need to do that by our tools. SD-Accel is a tool for high-level synthesis from Xilinx, and this is their flow of processing for this tool. So they start with the host code and unoptimized kernels. The kernels are not optimized in terms of memory access and data path. So these two flows are basically explaining how the memory access can be optimized by basically by grouping accesses from the software, from the application part, such way to be able to group them into bursts to maximize the usage of the memory channel, memory communication channels. So basically, from this optimization, we can hope to have 100 to 1000x speedups. On the other hand, data path optimization is not that promising in terms of speedups, but of course it's worth investigating, and this is mostly related to the local memory organization into banks that are specific to these FPGAs. So, OpenCL is easy to transfer to FPGAs because both Xilinx and Altera, which are major FPGAs vendors, are supporting this input. OpenCL allows to replicate workgroups to pipeline work items, which leads, we will see if this leads to an efficient hardware implementation. And they also allow to automate design space exploration, especially for loops within a work item and for local memory optimization. Especially then, particularly SD-Accel for Xilinx allows to do at the high level, so at the source code level, functional debugging, which speeds up verification, and to do cost performance analysis through design exploration, but this is mostly manual and requires some hardware expertise. Moreover, Xilinx provides open source kernels via university grants. Their intention is to develop, to foster an ecosystem around OpenCL-based FPGA acceleration. And they provide a large library of such kernels that are already optimized for FPGA implementation and include synthesis scripts. And this is for a few important areas, of which we have tried to implement on FPGA. A few of them, for instance, some financial algorithms, which have the characteristic is that they use local memory, not global, so they reduce the communication with the global memory. This is important and is a bottleneck actually for the FPGAs compared to GPUs. We also have applied this to machine learning algorithms, for instance, the key nearest neighbors, which again have limited global memory access. Actually, this needs to have global memory access, so it's not has no disadvantage to with respect to GPU. And for sorting, which of course is limited by global memory bandwidth, because they have, of course, to access all the memory locations for sorting them. And in this case, anyway, we'll see that FPGAs use less energy. So for instance, for an application that is using, this is for financial markets, so this is especially is working on the same set of data which, for which it generates random variation. We can see that a couple of GPUs are actually doing the work much faster, but they consume a lot of power and energy, while an FPGA on the low line of the table, we can see that it has more execution time, but it reduces the consumption of energy and, of course, also of the power. The FPGA in this case is competitive because it saves, because global memory is not used. In this case, we can see that this is the machine learning algorithm, K nearest neighbor. And in this case, we have a very good performance from an FPGA because, again, it's using streaming, and the global memory can be mapped on chip, whatever is needed to use. And we can see that in terms of energy, it is much more advantageous than GPUs. So basically, this is an ongoing project. You can see at the bottom the link to the project page. We are hoping to, actually, we are working to extend this, this tool set in order to automate also the design space exploration such way that the flow, the flow for FPGA acceleration of the computation will be fully automated and will hide as much as possible the hardware architecture for the software for the software programmers, so simplifying the adoption. These are some open points in terms of exploiting as much as possible the global memory access by using burst, so grouping the accesses in, to make use of burst transfers, and of course to expand this to other application domains. Thank you.
So OpenCL is theoretically a standard. Have you tried running the same kernels on Altera devices as well as Xilinx?
Sorry?
So you've done some benchmarking of your kernels on Xilinx devices. Have you also tried running the same kernels on Altera devices?
Yes, basically we need to make very few changes, if any, to OpenCL.
Okay.
Hi, Andre Pal. Some time ago, I was actually involved in part of the verification for a GPU for a company, which we won't talk about. We were using Vertex 7 2000Ts, and we were completely filling them. Do you have the same kind of thing?
You completely what?
Completely filling the Vertex 2000Ts.
Completely?
Completely. Yes, trust me, 98%. I did the synthesis.
Sorry, you completely, sorry?
We completely filled each of the Vertex 2000Ts.
Okay.
So that was one problem that we had. Also, part of that was actually part of the communication system to get the data out from and into the GPU for testing it. Now, you will have the same kind of problem. How did you solve it?
Yes, the communication is a problem, so we are hoping at most to, sorry, can you hear? Okay. So we are trying here to fill as much as possible the data path, the communication. Of course, the bandwidth of that communication is limited. One way that I heard in this project that they are using is to use the Unimem. Unimem is from the Euroserver project, is a kind of accessing the memory. Actually, it provides unified access to memory without making a copy to the user. They provide access to the memory in place. And that may be one way. The other, as I said, is just to reorganize the application in such a way to use as much as possible this channel. Of course, we cannot go beyond this channel. However, even if the computation is slower, which means that it can be split on more, on more FPGAs to become faster, what we are interested here is the saving in energy, computation energy, and that still stands.
Okay, I got a question. So FPGAs are usually less energy efficient than an ASIC, and the GPU for me would be some kind of thing that is built to compute things. So how on earth can the GPUs use so much more power than a FPGA doing the same thing? I really can't understand that.
One reason is because GPUs are general purpose. That means that they still have to fetch, decode, and execute instructions, and that is a lot of switching inside for every cycle. One reason for that.
Yeah, cool. Do we have any more questions? Well, let's give a thanks to the speaker.